Thanksgiving. Today, it's really a great pleasure for me because I'm introducing someone I've known for a long time, Professor James Cryan from Photon Science Department at SLAC is here. Let me just tell you a few things about him. James is a native of Ohio, and as someone who spent a lot of time at Michigan, I had to swallow that. He graduated from The Ohio State University in 2007 and came here where he got involved in the experimental side of LCLS, which hadn't yet turned on. So he was kind of in on the ground floor. He did his graduate work on experiments at LCLS. In fact, he was the first student to publish a student-led project on LCLS, got the first PhD that has come out of the machine, and won the Bill Spicer Award for outstanding thesis in X-ray science. And then for his postdoc, he went off to Berkeley, where he worked on the next generation light source, which never came to pass. After a couple of years, that got canceled, and he moved over to the Chemical Sciences Division in LBNL, where he worked with Roger Falcone and Ali Belkacem on building big lasers, but not X-ray lasers, obviously. Returned to SLAC in order to get involved in an interesting future project on the machine, which was to generate attosecond pulses. He and Aggo Marinelli, who's also given talks here on the attosecond pulse generation, formed a collaboration to figure out how to do science at the sub-femtosecond level using X-rays. Very successful project. Now about half of all of the experiments in gas phase targets at LCLS use the attosecond capabilities that he helped to develop. His management position there, he became the head of atomic physics at LCLS and also leads the TMO instrument area there. Today, he's going to talk to us about what's been happening and what the future is for attosecond science at free electron lasers. James, thank you.
Thank you. Thanks, Phil. Thanks, everybody, for coming today and to listening to what I have to say about what we're doing at SLAC National Accelerator Laboratory. Here you can see the nice flyover view. I think this is a new picture that we've taken now that we can see this side, looking down from the injector, looking down the entire Linac, and we're way off kind of in the distance. I think you can even see the Hoover Tower there at the end. But anyway, so I'll tell you about the exciting things that we're doing. I think one of the most important things is that this thing works. So let me try again, since it seems to not work. Let's see, hopefully this time. This time, yeah, no, maybe. Uh-oh. Okay, well, anyway, I'll do this. Oh, wait. Okay, here we go. Nope, still not working. Okay, well, we'll do it this way. Oh, maybe it's the Zoom. Okay, so I want to start by thanking all of the people in the group. I tend to try to jam a lot of things into these talks that I'm excited to tell you about. So the first thing that I want to do is to tell everybody, or to thank all the people who are doing the work, and maybe, so you can see that better, I need to get rid of this thing up at the top. There. Okay, great. I want to thank all the people. So working on attosecond science at LCLS, this is a group who is led by Agostino Marinelli, who I think was here maybe a year ago giving the same colloquium, myself, along with Phil Buxbaum, and also Taryn Driver, who is a staff scientist. We work with a variety of Stanford graduate students, but also permanent staff at the lab. You can see these national lab projects tend to be very large, big collaborative works. This is why you see so many principal investigators. You also see over on the right, we work with a broad range of collaborators at different institutions. And even I'll show you work that was done by students who have graduated, who are shown over here in the gray, just because they have moved on to other things. But they still have a lot of work. It's not that they've passed on. They've just moved on to other things. But they don't work on the same thing as us anymore. Okay, so these are the people whose work you're going to hear about. And this isn't going to advance slides. There. Okay. I also, as Phil was saying, lead the AMO Sciences Department at LCLS. So this is a department of 6 staff scientists that support the efforts of atomic physics, atomic molecular and optical physics at LCLS. And so what is the thing that we want to study? So I'm going to start with this movie over here on the right side, which is done by one of our theory collaborators at the University of Madrid. This is showing a small molecular system. This is a benzene ring with an amine group or NH2 group on one side and a hydroxyl group or an OH group on the other side. And to do this calculation, they have very quickly removed an electron. And then what they're doing is they're plotting the charge density around this electron as a function of time. And so they're doing this in a differential way. So they're comparing to the ground state charge density. So red is representing an increase in the charge density, and blue is representing a decrease. So the first thing you can see from this movie is that right after you remove this electron, the charge starts to move. And it starts to move around and oscillate and slosh back and forth across this molecule. And you can see that it does this on a rather extreme time scale. You can see this little clock up at the top. It's ticking by with femtosecond time scale, which I'll come back to in a second. But one thing that is very important about this movie is just by watching it, we know right away that it is wrong. And why is it wrong? Because it had an assumption to make this, to solve the electronic problem at the level of precision that they needed to get this movie to look what they think is right. They had to freeze the nuclei. They could not let the nuclei move. But we know as soon as we start to change charge densities and change what's the electron density that is bonding atoms together, those atoms are going to start to move. And that's usually what we call chemical motion, atoms starting to move in response to changing electron density. And so what we really want to study is how does this nice oscillating charge motion that looks really cool, and you can sit and watch it for a while and say, oh, that's really interesting. How does this turn into longer timescale chemical motion and yield results that change the chemical activity of a molecular system? And then how can we track this on this intrinsic timescale? And to get another idea of this, here we can play this movie, but instead of playing it in time, we can look at the electron density in different places. So with the red line, I put a little box around the oxygen atom, and I say, what's the electron density there? And with the blue line, I'm going around the nitrogen atom. And the green is showing me what's happening around the carbons. And you see, now I start to get a more full picture that if I really want to understand this charge motion, not only do I need to get to an extreme time scale of sub-femtosecond type of resolution, as you see on the x-axis, but I also need to be able to look at the charge in a site-specific way. How I want to know the electronic density around the different atoms in the molecular system. And so I need both of these if I want to make this measurement. And why do I care about making this measurement? Well, this fundamental charge motion, this motion of charge back and forth across molecules, this plays a role in a lot of very basic, or in a lot of very important processes, right? Electron motion is responsible for how we harvest light energy in, say, photochemistry. And so we want to understand how does this kind of oscillatory motion that we just looked at in this molecule, how does this turn into other real chemical type of motion that we care about? Or how does this lead to molecular electronics? So this is kind of the end goal of where we want to be. And so before we get there, I want to take a step back and go over a little bit with timescales with everybody in case people are not as familiar with molecular timescales. So when we start thinking about molecules, the first thing they can do, they can rotate. And based on the energy spacing between the rotational states of a molecule, we find that molecules rotate on the time scale of hundreds of picoseconds, tens to hundreds of picoseconds, depending on the size of the molecule. And then the next thing we can have is, instead of the body motion, we can have internal motions. And so this is vibration. So molecules can vibrate, and they tend to vibrate on the time scale of tens to hundreds of femtoseconds, again, depending on the size of the molecule and the size of the mode, or the size of the mode. And then finally, we get down to this electron motion that we were talking about. So this, I was just showing you. So on this few femtosecond, even sub-femtosecond time scale, I start to see the motion of electrons back and forth across the molecule. And again, this is set by the natural EV scale binding energies of electrons. And then finally, I can go down to these core level electrons, the most strongly bound electrons in a molecule. And these tend to have oscillations on the timescale of few attoseconds. And so this attosecond, this 10 to the minus 18, I can put it into more relevant units. I could say, well, the speed of light in this relevant unit is about 3 angstroms per attosecond. So that means that light will move across my molecule in about 1 attosecond. And then on top of that, I could do this. I really like this SAT comparison, although I don't think many people take the SAT anymore, so it might not land anywhere. But 2 attoseconds is to a second as a second is to the age of the universe. And I think we originally found, well, we've seen this comparison, and I was writing a review article with Phil, and we're like, well, is there anywhere else we can find the word atto in literature anywhere? And it turns out that in cosmology and expansion, you can talk about attohertz in terms of the expansion timescale. So we found a paper that referenced that, and somebody else is using atto. Okay, so there's also fundamental questions that we can answer. Say going back to this 2005 paper from Lynn Cederbaum's group, where they asked this very general question about, is there some sort of universal response to this ionization type of experiment? If I remove an electron, they found by calculating in 3 different systems, they started with an atom, a simple molecule, and a larger molecule. They see on this kind of 50 attosecond time scale, they saw this kind of common behavior that they wanted to call this universal response, where they attribute this to, they remove an electron, and what initially happens is this electron cloud has to realize that it's no longer in a neutral molecule, but it's in an ion. And the ionic wave functions look different than the neutral wave functions, so it relaxes. The wave function spreads out. And so this led to, there's a bit of controversy in literature about, is this actually a real measurable effect? Or is this just an artifact of how you do calculations? Is this something that we could actually measure? Or is this just when you use this basis set to do this calculation, you get this type of result, and different basis sets would tell you different things? So if we could push to these extreme timescales, we could understand, is there really a universal attosecond response? Then you can see after this kind of 50 attosecond timescale, things begin to get different. Different molecules will undergo different charge motion, and different things will begin to happen, okay? And so because of all of this importance of the electronic motion and the extreme timescales that it takes to get to probe these motions, this led to the 2023 Nobel Prize in Physics, which was awarded to Anne Louier, Pierre Agostini, and Ferenc Krauss. I think all 3 of them have actually been here to give this colloquium. Anne was here a month ago, 2 months ago, and she was the last of the 3 to actually talk to us about what they had done. And so in the inscription, they were given the Nobel Prize for fundamental methods that generate such short, extreme pulses, but it wasn't just the generation. While yes, this was a very technical award for leading to the methodologies that make short pulses, it was really because they can study electron dynamics and matter now that we couldn't do before. So it was very important in that way. So it's not just the technological advance, but it's also what we can start to study now. And so like these movies and pictures that I showed you at the beginning. And so now we need one final ingredient if we really want to look at these electron motions, right? I told you we need to get to extreme timescales, but we also want this kind of site specificity or element specificity of the electronic motion. So we can do this by going to X-rays. So if we look at how X-rays interact with matter, here is looking at a cross-section of, say, just a carbon atom. And you can see once you get above 300 eV, the strongest interaction between the atom in the light field would be these 1s electrons, so the very tightly bound, localized electrons in the molecule. Now, if I take some carbon atoms and stick them together to make a molecule, and I maybe put some other atoms on there, I can see it's not just that these core level electrons are very tightly bound and have a large binding energy, but also that their binding energy is to some extent controlled by their local environment. So if I take a carbon atom, like on the right side of this molecule up here, and I bond it to 3 fluorines, these fluorine atoms are very electronegative. They withdraw the electrons. They pull the electrons in, so they create a lack of shielding of this core level electron, and it becomes bound more strongly. Versus if I bind to a bunch of hydrogens, which are not as electron withdrawing, I see that I get more shielding of this carbon 1s electron, and its binding energy is lower. So now by looking at these core level electrons, I can find out what the local electronic density is like. I can understand, I can start to make this movie that I was showing where I need to resolve what's going on at a nitrogen atom, what's going on at an oxygen atom, what's happening at different carbon atoms. So I can start to do this by looking at the binding energy of these electrons. So this leads to, what do I need? I need an attosecond source that also produces X-rays. And so here you can see, I play this movie again. I've changed the color because it's easier to print, actually, when you do in this color. The journal likes it better, apparently. But here you can see the snapshots of the same charge density. And then in the green line, I show you the charge density. I show you what the charge density looks like. And then with the black line, I show you the near-edge oxygen absorption spectrum. So this is the intensity of oxygen absorption as a function of time for the same molecule, and maybe not surprising, given the last slide, these two match very well, showing you that even when I have this time-dependent density, I can also see this kind of charge oscillations using X-ray absorption. Okay, and I can zoom in at, say, just the oxygen atom and ask what's happening there, which is what I've done in this picture as well. Okay. So now I want to go ahead and say, let's start making attosecond X-ray pulses. And if you look back at this technology that led to the 2023 Nobel Prize, which was called high harmonic generation, where I take a strong laser field and I focus it down into a gas, and I drive a highly nonlinear process to make X-ray pulses, which I can do, I find this rather discouraging trend. That as I want to go higher and higher in photon energy, my pulse energy, or my ability to create lots of photons, goes down and down. And it has this rather, as I get to this kind of 500 or 600 eV where I can access oxygen 1s electrons, I have almost no light. So this is kind of a limitation. And this is likely due to many factors, one of which being that in this strong field ionization, I think both Pierre and Ferenc talked about this in this colloquium series. There's this electron wave packet that tunnels out of the atom and propagates in a strong laser field where it picks up energy. But the spread of this wave packet laterally as it gains this energy means that the recombination efficiency is very poor. So most of the time, I'm not able to make photons using this process. Now, this is kind of discouraging. Luckily, I wouldn't have a talk if there weren't another way to do this, or this would be a really short talk and I could just end and say, so we'll never do it. But we have another technology, and this is called X-ray free electron lasers. This is what we've built at SLAC. This is what Phil was talking about in the introduction. The one here at SLAC National Accelerator Laboratory is called the Linac Coherent Light Source, or LCLS. This is we take a relativistic beam of electrons and we pass it through a magnetic device where the electrons wiggle and they give off radiation. This radiation is at X-ray wavelengths. And then because we have such a big facility, we actually couple it to a number of different end stations. So here you can see an overview of our facility. We have 8 different end stations, all of which have different capabilities. They say service different wavelength ranges of the X-rays. They have different capabilities. Say we can look at molecules in solution. We can look at solid state samples. We can do scattering experiments. We can do spectroscopy experiments. The main experiments that I'm going to tell you about happened in what's called our TMO end station, or our time-resolved molecular and optical sciences hutch, which mainly looks at gas phase systems. And it mainly does this with soft X-ray light. So I'll tell you about soft X-ray spectroscopy, which is what I've been describing, in gas phase molecules. Okay, and so getting the FEL to go from typical FELs makes something on the order of 100 femtosecond pulses. To push down to this sub-femtosecond barrier to really start to look for electron densities, this was really kind of the brainchild of Agostino Marinelli when he came to SLAC. I think he started as a staff scientist and then was a Panofsky Fellow before he became an assistant professor in photon science. He had this this idea of how we could make these short pulses with the FEL, and this got us really excited to work together and to develop all of this. So all the things I'm going to talk about were actually done in collaboration with his group to really push to this attosecond barrier. And now we can add our source to this list that I showed you before, and you can see, probably because I made the plot, right? And I'll give a disclaimer that there are many axes on which you can plot a light source. I have chosen two of them, photon energy and pulse energy. And I've chosen these two because my source, the red ones, show up in the upper right, which is where you want to be. So I have picked axes that are favorable to my source. And when I then show them on this axis, great. But I think these are actually useful axes if we want to kind of get to these ability to probe these inner shell electrons, to probe 1s electrons, and also if we want to, say, drive nonlinear interactions. So one simple nonlinear action to think about is I first interact with a pulse to create that movie that I'm looking at, and then I come in with a second pulse to probe what's going on. And then by changing the time delay between those pulses, I can map out this movie. So this is exactly the first experiment that we set out to do. And so I'm going to tell you about two experiments that we've done so far. The first is trying to make this movie of this aminophenol molecule and this charge density oscillation. And the second I'm going to tell you about is really related to what Anne talked about in her colloquium when she was here, of probing the photoelectric effect on these attosecond timescales to really see that, in fact, photoionization is not instantaneous. And when we can push to extreme timescales, we can actually resolve very interesting phenomena that happen as electrons are freed from molecular systems. So when it comes to trying to make this movie, the first thing we need to do is not just generate one pulse of attosecond X-rays, but actually generate two. Right? So this was the big problem. Ago and I first made this pulse, and we said, okay, we have an attosecond pulse. You take it to an ultrafast laser scientist, and the first thing they say is, great, can I have another? Because I need to do something where I first initiate and then I probe. So we came up with a scheme to actually create two laser pulses. So here you can see we take these undulator devices that make the X-rays, we split them into two groups, and then we can use one to make a first pulse, a pump pulse to initiate the dynamics, and then a second pulse to probe the dynamics. And so this is exactly what we did. We come into this aminophenol system, and we ionize these outer valence electrons to induce this charge motion. So we tuned this first X-ray pulse to be low enough photon energy that it doesn't interact with core level electrons, only valence level electrons. And then we induce this charge motion. Then we come in with a second pulse, our probe pulse, and we try to look at absorption at the oxygen K edge to understand what's going on. And so you can kind of visualize this in this picture. This is not entirely accurate when it comes to electron configuration interaction, but you can kind of think of it as we generate a hole in the system with the pump pulse, and then we come through with this probe pulse and tune around the energy till we can fill this hole, till we can excite a core level electron into this vacancy. Then this core level excited state, this highly excited state, is going to decay, and it decays through this process called the Auger-Meitner process. Basically, two electrons interact. When they interact, one electron fills this core level vacancy, and the other electron is ejected with the excess energy. So this will create high energy electrons in a leftover cation, and these high energy electrons are what we record. And you can see our measurement here on the right side. As we scan the photon energy, we can record the electron kinetic energy, and we can see this nice kind of dispersive feature right here. This is just ionization. This is valence level ionization. And then we hit a resonance where actually this X-ray pulse is tuned so it doesn't just ionize the molecule, but rather it hits an intermediate state that I didn't draw in this picture. So if I hit one of these intermediate states, I get a big absorption, and that's why I get a lot of electrons. Now, for our measurements, we're not actually going to worry about this kinetic energy spectrum. We're just going to count electrons, because if we count an electron, that means we absorbed a photon. And so the next thing we can do, because we have a bit of jitter, we can sit there and we can bin our data. And we can bin our data based on the intensity of this pump pulse. And so right here, what you see are three different pump pulse energy bins, and you can actually see we actually have a lot of them. When we integrate over this blue region here, you get the blue dots. This is the pump pulse energy. So as the pump pulse energy increases, this absorption feature that we see gets larger. This is indicative of you have something that depends on the probe pulse being there because it absorbed it absorbed a 520 eV photon, and it depended on the pump pulse being there. So this is our two photon signal that is a pump probe signal. And so this was done, this data set on the right was taken when these pulses were very close in time. So then the next thing you want to do is just take these and say, well, let's now map out the time dynamics. How does this absorption change? And so what we see is this plot as we record for time delays. We see this on the few femtosecond time scale, this very fast drop in the absorption. So this blue line right here is looking at the absorption in this blue region right here. The green and the red lines are looking further down. So the green line is looking in this region right here, and the red is looking to the left, just to show you what 0 looks like, that there is a little bit of change, showing you what our noise spectrum looks like. So we see on this few femtosecond time scale, we see this rapid drop in the absorption feature, and then it revives. It comes back up around 5 femtoseconds. And so to understand what's going on, are we actually seeing this charge movie that I've been showing you? We worked with 2 different theoretical groups to calculate what was going on. So this group from Imperial College, led by Marco Roberti, and also this group from Madrid, led by Fernando Martin and his postdoc Gilbert Grell. Both groups did calculations of what we expect these dynamics to look like. And so you can see these here. You can see our measured photoelectron spectrum. So this is just modeling the interaction with the pump pulse. And so our measurement is shown in black, and you can see the 2 theories. In green is this measurement from, or this calculation from the Madrid group, and the purple is from the Imperial group. And you see that largely these agree with our measured spectrum. Everybody's getting it most of the way right. Maybe the green spectrum agrees slightly better. And we said, okay, that's great. We have a good, we can calculate what these photoionization cross-sections look like. And so this is related to the population, right? The photoelectron spectrum is related to the population of the cationic states we produce with this X-ray pulse. So we can get the populations mostly right. Then we also see that both groups try to interact at the short time delay. They also try to interact with or try to calculate what the probe interaction looks like. And here you can see, again, they both get very good agreement that we would see an absorption feature around 520 EV or so. So they both agree there as well, and they agree with the measurement. Then we said, okay, this is great. They both went ahead and did the time-dependent calculation to see what happens as they scan the pump probe delay. And this is where we saw something really interesting. These 2 curves, for both of them, look nothing alike. So even though they both got the populations right, they both understood the population because they got a roughly good estimate of the photoelectron spectrum, they disagree a lot on what the phase looks like. Well, that's what we're able to do with time-resolved spectroscopy, is we're able to look at phase evolution, phase differences between states as a function of time. And we see that these 2 theories don't agree very well on the phase evolution. So now we want to take this and compare this with our data and say, okay, so which group is doing this better? Which one is getting closer to the right answer? And now if you look again at our data set and you look at the calculations, you say, ooh, none of these kind of look quite right. Well, that's because when we first approached this problem, it was actually a little bit too simple. We said all we're going to do is we're going to induce this charge motion and watch the charge oscillate. Of course, that can't be all that's going on. We also can create states. So these high binding energy states, they actually live above what's called the double ionization potential. So that means if you created a cation that is higher in energy than the lowest lying dication, they can undergo this process, this Auger-Meitner process. In this case, it's called Koester-Kronig decay. And very quickly, they can decay to produce another electron and form a dication. So this signal is also going to be in our data. And it actually produces an absorption feature that's very close in energy to the absorption we observe. So both this charge density oscillation and this electron correlation effect are both going to be in our data, and we have to model both of them. So once we include this in the model, and we include another empirical factor for the fact that both of these calculations needed to leave nuclei fixed, which we know is not going to happen, right? We already talked about chemical motion is a thing. So as the nuclei move, of course, these absorptions are also going to change. So we include an empirical effect of the nuclear motion. Now we can see both the green and the purple, the dark green and the dark purple curves are the two calculations. And unfortunately, now things look very similar, and it's hard for us to tell which one of these calculations is better than the other. Now, this is limited mainly by our data. We have 10 delay points that we took. Now, this took us a week to collect this data because our original free electron laser runs at 120 pulses per second. When you need to get to something like 1 million shots of the laser to get a good data set, it takes you a long time to build up frames of this movie. Fortunately, I'll talk a little bit about at the end, we've just undergone an upgrade at the free electron laser, and now instead of doing 120 pulses per second, we can do 1,000,000 pulses per second. So now instead of taking a week to make 10 frames of a movie, we can do this in less than a day. So this is really exciting for the next steps to try to differentiate these movies. Since we haven't done the next step, the other thing we were able to do is compare two different molecular systems. We looked at this para-isomer where the amine group and the hydroxyl group are across from each other in the molecule. When we do this meta-substitution, this isn't the chemistry colloquium, so it's not so important that we go too much into this, but when we do this meta-substitution, we actually change all of the electronic structure, the nodal structure of the electron wave functions, and that will change the electron density oscillations. And so we also measured this isomer, and we see that there's general agreement that this decay is very fast in the first few femtoseconds, but then this kind of revival feature or this increase in the absorption doesn't really happen in the meta-isomer, which was interesting to see. And together with this, we can kind of get this idea, we can start to approach this idea of this universal response to an impulse. Can we actually get down? Of course, we're not quite there at the timescales that I talked about in the beginning, but we're starting to approach this and get close to these timescales. But the results here are not just important for X-ray ionization, but actually any kind of fast ionization process could lead to these kind of charge densities. So this could be electron impact or ion impact. All of these kinds of ionization events will lead to this generally broad wave packet in the ionic state that will have this Koester-Kronig decay that happens on very fast timescales, this charge density oscillation before eventual chemical motion kicks in. Okay, so now I've talked a bit about what we've done to look at ultrafast charge motion and using this X-ray pump, X-ray probe type of technique. Now I want to talk a little bit about resolving the photoelectric effect, which we can also do on these attosecond timescales. This is something I think when Ferenc Krauss was here, he used this term attosecond chronoscopy. And so to talk a little bit about this, the infrastructure or how we do these types of experiments, we take a very short X-ray pulse and we overlap it with an infrared field. And our target molecules, so the X-rays and the infrared field and our target molecule are all sitting together at the interaction point, and then we measure the electrons that come off using an electron time of flight spectrometer or some other type of electron spectrometer so we can get electron kinetic energies. We know from, say, basic E&M that the constant of motion is the canonical momentum, which is the mechanical momentum plus the vector potential. And so we can say since this is a constant of motion, we know that if we create an electron with some momentum p at some time t naught, then the momentum that we measure at some time t equals infinity after this vector potential has gone to 0, after the laser field turns off, is going to be equal to the initial momentum plus the vector potential. And you can see that in this measurement here also from Ferenc Krauss's group. This is showing an electron energy spectrum measured as a function of delay between the X-ray and the laser. And you can see it maps out this sinusoidal oscillation, which is the vector potential of the laser. So we can get this very precise timing information. Now, we don't use the linearly polarized field. Actually, we use a circularly polarized field for our measurements. If you have questions about why circular polarization is better than linear, I could talk about it at the end. But the important thing is we're using a circularly polarized field. So instead of the vector potential amplitude changing in time, rather it has a constant amplitude in a changing direction. And the direction changes that it's undergone one oscillation in the laser period. So we're all pretty familiar with using angles to tell time because we've all looked at clocks, right? This is the idea behind a clock, is that we map some oscillation and angle maps to a time. And so this is exactly what we've done for the attosecond timescale. We can map changes in angle of the vector potential to time because we know the period. And so we can use this simple formula to get a time delay by looking at an angle difference when we look at this angular distribution. And so this movie right here is actually a measurement that we've done where we took the X-ray pulse, we took the laser pulse, and we scanned the arrival time between the laser and the X-rays, and we see this electron density makes this nice circular pattern as we scan that delay. Okay. So then we went from, this was actually done in an atom. This was done in a neon atom at 900 eV. Then we went and we looked at a molecular system. Well, actually, let me tell you first, I forgot, I should tell you this. How we usually visualize this data is not in this movie. While it's pretty and fun to watch, it's not the easiest way to visualize this data. Rather, what we do on the left is a panel that we collected, a photoelectron spectrum that we took in neon when we had no laser field there. So this is just what you would measure from 1s ionization of neon. You get this characteristic outgoing P-wave distribution, which has this two-lobe structure. Then when we add the laser field, you see that this distribution gets blurrier and it shifts. And to highlight this, we can subtract those two, and you get in the subtracted view on the right, you see that in this particular shot, the vector potential was going down and slightly to the right. So you see this increase in electron density over to the low right side and this decrease in electron density on the left side. So this is an easier way to visualize this. So when we go to our molecular sample here, we use nitric oxide, which is a nitrogen atom and an oxygen atom stuck together. And then we scan the photon energy, and we can see we get this very low energy electron. This comes from ionization of the oxygen 1s orbital. And we get this higher energy electron or higher momentum electron. This comes from the ionization of the nitrogen atom. And we can measure the relative angle between them. And I try to highlight this with these two arrows of what's the difference in the angle that the electrons are pushed by the laser field. And you can see that it's changing as we change the photon energy. This is telling us that the time at which these electrons show up in the continuum is changing. So we actually have a delay between this fast electron coming from the nitrogen and the slow electron ionized from the oxygen 1s. Okay, and we can map this out and show it as a function of kinetic energy. And so up here for the high kinetic energies of the oxygen, so this is the kinetic energy of the oxygen 1s, this low momentum electron. We go up to 20 eV and we come down to close to threshold, close to 0 eV. And you can see that this goes from something like 100 attosecond delay up to almost nearly a femtosecond. And so how do we understand this? Well, we can kind of understand this theoretically, typically, and I think Anne again talked about this, so I'm just going to hope that you recall some of the things she spoke about. Typically, we take these delays and we break them into two parts. This first part is what we would call a single photon photoionization delay. So this comes, we'll talk about the origin of that, but this comes from the dipole matrix element. It's actually related to the phase of the dipole matrix element. Then we have the second term that we usually call Coulomb laser coupling or continuum transitions. This is a measurement-induced delay that has to do with the fact that as the electron is leaving, the Coulomb potential is long range. It's not finite. So when you're interacting with that laser field, you're also in the presence of the Coulomb field. No matter how far away the electron is, you still have some Coulomb potential that you're fighting against. And so that leads to this measurement-induced delay. But of course, we can model that. And we worked with a group at Ohio State to model this for our exact situation of this X-ray ionization, because we can look at fast electrons just propagating in a potential. So we can start by just saying, well, if we just had an atom, we can go and we can write down what this single photon matrix element would look like. And we can come up with a delay. And it has to do with this argument of this gamma function, because this is just an electron propagating in a Coulomb potential. And you see, if we only had a Coulomb potential, it does describe kind of the base idea that at high kinetic energy, we have low delays. And at low kinetic energy, we have high delays. But other than that, it really looks nothing like our model. Or it looks nothing like our data. And this means that there is more going on, right? The fact that it's a molecule matters. It's not just that it's a Coulomb potential. It's not just that it's climbing out of a charged well. So we worked with a group at University College London, and they had done some Hartree-Fock level calculations to try to understand what was going on. And the first thing they saw in these calculations was this bump in the delay. And this bump is due to a kind of interesting phenomenon. This is a transient trapping of an electron. So as the electron is ionized, it's actually ionized into a very high angular momentum state, and it sits there and circles around the ionic core for a little while before it eventually tunnels through this centripetal barrier and leaves the molecular system. This is what's called a shape resonance. So they predict that there's this shape resonance in here. Now, I say this is actually Hartree-Fock. They actually had to go a little bit beyond Hartree-Fock. So remember I talked to you about this thing at the very beginning where this Lynn Cederbaum's group was talking about this universal attosecond response. This kind of idea that the cationic states, the wave functions of the cationic states and the wave functions of the neutral are not the same. This actually has to be included for us to get this shape resonance. So we actually have to use in this calculation the wave functions of the ionic state, not of the neutral state. Otherwise, we don't get this shape resonance at all, and we get something that looks very much like the Coulomb curve. So there's already this effect of electron correlation, and we're seeing this kind of universal attosecond effect, even though we're not probing these timescales quite yet. These are still hundreds of attoseconds, not down to this 50 attosecond, but we have to include this process anyway. Then we worked with the group at Berkeley Lab, and they can actually go even further and not just do a Hartree-Fock style calculation, but use multiple coupled electronic states. So start to include the fact that electrons will interact with each other when they do this. And they can do this not just with 2 states, but actually with all the way up to 7 states. Now still, these are still pretty far off from our measured delays. There's one more effect that is worth talking about, and I kind of already alluded to this. This is actually the fact that once we remove this core level electron, it's in a very unstable state. And this will decay via the Auger-Meitner process. Now you have this interesting interaction that you have this slow photoelectron that you ionized from the core. Now this Auger-Meitner decay happens, and you get a fast electron that comes zipping away from the core. And at some point, they will pass each other. And when they pass each other, they can interact. And now this slow electron no longer feels like it's climbing out of a singly charged potential, but a doubly charged potential. This is called post-collision interaction. And we came up with a semi-classical model to describe this. And we can see that based on electron delay, based on the electron kinetic energy, we will get a different effective delay from when this electron passes over. So when does the electron look like it's leaving a cation to when does it start to look like it's leaving a dication? So once we include this model, you see these curves shift a lot more and we start to look a lot more like the data. We're still not quite there. We then do a calculation where we don't just include 2 states, but we actually include 7 different channels. And now we can get pretty good agreement with our data until up to about a kinetic energy of 10 eV. And that's surprisingly, or that's maybe not surprisingly, that's where our highest of these 7 channels was around 10 eV. So probably we believe that including more channels would have gotten better agreement further out. But this was already enough to say we now understand what we're doing in these measurements and that we actually are seeing the interaction of these different electronic channels as the photoelectron is leaving. So it's not just as simple as we create an electron and it leaves the system. When it gets stuck in the shape resonance and is circling around the target ion, it still interacts with these electrons and exchanges energy. And we can visualize this a different way. So we can really think of this electron propagating out of the molecular potential, much like we'd think of a light wave. When a light wave goes through a material, it has some index of refraction that it depends on its wavelength, on its energy. So we can reshape a light pulse as it goes through a material. We're doing the same thing. We are reshaping an electronic wave function as it propagates through the molecular potential. And so this cartoon here is kind of showing you the base level definition of a delay, right? We'd have 2 wave functions, one that propagates in free space, the other that goes through a potential, and you see that when they get to our detector, they actually arrive at different times. This delay is the first thing that we can measure, but we also see in these pictures that this electron wave function gets reshaped. And we can use our data, we can use this delay information, we can differentiate this, and we get effectively a group delay dispersion for the electron wave packet. So we can understand how the wave packet is reshaped by the molecular potential. Or we could actually integrate the delay we get, and now we get back to the phase of the wave function. So now, because we have the cross-section, we have the photoelectron amplitude, and we have this delay measurement, we have both the amplitude and the phase of the continuum electron, so we can completely reconstruct this. And now we can make a Wigner distribution for this outgoing electron. And so here we show the Wigner distribution in the case of a molecular potential, and we compare that to what we would get if we just had an atomic potential. And there's a lot of things that looks very similar here. When we look around this region of the shape resonance, kind of right in here, we see this kind of trailing edge. This is showing this part of the electron density that's getting trapped near the core as the rest of the density moves away. I can make this a little bit easier to see by looking at the marginal distribution. So I just sum over the kinetic energy, and the atomic potential gives me the gray or the brown curve up and to the left, and the black curve gives me is what I get from the molecular potential from our data. This is actually reconstructed from our data. And so you can see the major effect is this delay. They're offset in time, but even if we shift to compensate for this delay, there's still this reshaping due to the propagation in the molecular potential. So all of the things we think about with light fields propagating through mediums, we can now start to apply to electrons leaving leaving molecules. And we've done a whole bunch of other experiments that I just wanted to highlight, looking at coherences and looking at these kind of coherent oscillation of charge using core excited states. But the last thing I really wanted to talk about, and then maybe take some questions, because I think I'm pretty close to on time, I hope, is what we're doing with our upgrade to our facility. So in the last 2 years, we've been working very hard to commission a new linear accelerator at SLAC. This is a high rep rate superconducting accelerator. So instead of doing 120 pulses per second that led to this data that I showed up here, we can now do, we've demonstrated 30,000 pulses per second, and we hope in time we will actually get to 1 million pulses per second once we're fully commissioned. And so this will take data sets like I'm showing here that took us weeks to take down to minutes to take these data sets when we can do this type of five-fold increase in the repetition rate. And so we've already done some experiments with different groups. My group collaborating with other groups around the world. We've worked with Francesca Calighieri and John Marangos to look at differences in molecular structure by looking at different protein molecules and trying to do these charge oscillation studies. We've looked at long-range electronic coherence. So we've tried to drive electron wave packets by, say, ionizing a chlorine atom on one side of the molecule and looking at what happens on the opposite side of the molecule using this X-ray absorption. We did this with a group from KSU. And then we tried to look even at symmetry constraints by looking at small molecules with 2 nitrogens bound together versus molecules that have nitrogens delocalized across the molecule to see how the charge density oscillations change in these systems. And finally, we've been working very hard to develop nonlinear spectroscopy. So trying to look at higher order correlations, not just simply pump the molecule and probe it, but look at correlations between different parts of the molecule by using higher order interactions. So not just doing a pump and a probe, but rather interacting with multiple photons to get even more information. And so we have some initial experiments here that actually until about 6 a.m. this morning, we were doing another one of these, but the data is not ready, so I can't show it to you yet. But in any event, trying to make these charge density movies much like I showed you at the beginning. And so the last thing I just want to advertise before I finish is all of this. LCLS is a user facility. And so it's not just us doing all of this. Actually, all you have to do one of these cool experiments is write a proposal. And so if you're interested or thought some of this was particularly interesting, feel free to reach out to me, or I put some of my colleagues down here if you say, wow, you know what, that guy was really off-putting and I don't want to talk to him anymore. Well, I put down some other contact information for other people. Maybe you identify more with material science, or as a chemist, you could talk to our chemistry department head or our material science department head. But we have 2 proposal calls per year. So if you're interested in doing some of this, a lot of what we do as these department heads is work with potential users to develop science cases or to develop proposals for using the unique instruments that we have. We can do things both at soft X-rays. So for me, that means between 250 eV and 2 keV. This is where we're actually able to do the sub-femtosecond pulses at up to 100 kilohertz, but we also have a hard X-ray machine that goes all the way up to 25 keV, which we've also demonstrated sub-femtosecond pulses there. So feel free to reach out to me if you're interested to develop a proposal there. And with that, I'd like to thank the group of people who actually did this work, or who did a lot of this work. also the AMO department, and finally the TMO instrument team who supports user experiments and does all of these things. And so with that, I'll hopefully have time for questions. And thank you for your attention.